So we're going to start off today with a slope and a distance review. So take the time to calculate the slope and distance of the 3 line segments on the grid and find the slopes of the following coordinates. Okay, so when we're looking at the distance and slope of the following, I have a saying, it's when life gives you a coordinate plane, use it. So if you jump right into using formulas and whatnot, and that's your jam, and you rock it, good for you. Awesome, don't change. But if it helps you to see what we mean by slope, you should be able to look at these 3 lines from an algebra lens and say, one is negative and 2 are positive. You should say 2 are steep, and 1 is neither steep nor flat. Do you see that? Because our 1 negative decreases. We always read a graph the same way we do a storybook from left to right. So if I start here and I end up going down and decreasing, that's because I have a negative slope. If I start here and I go up, I have an increasing slope that's positive. These 2, my slopes, are steeper than 1. So when we look at steep versus flat, we compare it to 1. This one's kind of flat, but closer to 1 for sure. So when I look at the slope, I'm looking at my rise over run, up 12, and then 1, 2, 3, 4 in the negative direction, up 6, 4 in the positive direction, up 6, 8 in the positive direction. Now what I want you to see is when you move on from finding slope to finding distance, these differences that you found, these side lengths, are sides of a right triangle that you stick into Pythagoras to find the distance. A squared plus b squared is c squared. A squared plus b squared is c squared. And here's an interesting shot. Notice I did not simplify a single one of my radicals. You're like, you're breaking all the rules. We're going to talk about why in a minute. What's on your mind?
That.
We're going to talk about why. There's three things you can do with radicals. If it's super nice and it simplifies out, that's awesome. Oh, there's 4 then. Then you can simplify. If it has a perfect square in it, you simplify that radical so that you can abstract, multiply, or divide it easily because you're still working with that number. That's fine. Here's the next thing. If you're doing a word problem, like if somebody asks me how far it is to my house, and I say, oh, just continue down that road about route 160 square, or 160 miles. So I'd be like, how, I don't know what the square root of 160 is. You'd be like, oh, well, when you reach about the square root of 160, that's where you'll see my house. So if they're a person who has good number sense, you'd be like, okay, that's somewhere between 12 and 13, 144 to 169. But chances are, they're like, can you give me how many miles it is? Okay, we need to know it's 12 point, blah, blah, blah. So we estimate it in real life problems, because that's what's more realistic. We simplify it for math problems that I'm still working on, adding, subtracting, multiplying, dividing. But sometimes, like we're going to see today, it's almost easier if you leave everything unsimplified, because look how easy it is for me to see which is my longest, which is my medium, which is my smallest. A lot of times when we simplify the radicals, we lose that perspective because what's left inside the radical is different. If I was comparing 10 to 4 root 10, it's hard for me to know which one's bigger, which one's smaller, right? So it's nice when we can go ahead and see that third option of not simplifying. All right, so whether you do your slope snake or not, I used to not like the slope snake, and then one of the kids I tutored got me turned on to it, and they liked it because it made it easy to see. My x's are on the bottom, my y's are on the top. And if you're a kid who makes that mistake all the time, try adopting the slope snake as your new pet. Because if you start at the beginning and zigzag it, It puts your x's on the bottom, your y's on the top. And if you'll notice here, I did 9 minus 10. Here I did 6 minus 4. It doesn't matter which point is your first or which point is your second coordinate, as long as you're consistent. So once I did 9 minus 10, I had to do 4 minus negative 3. Once I did 6 minus 4, I had to do negative 5 minus 2. The only thing that happens if you switch order with somebody is your negative might end up in the opposite location of the fraction. If you made this your first coordinate and did 10 minus 9, you would have ended up with 1 over negative 7. But try it in your calculator. Negative 1 divided by 7 is the same as 1 divided by negative 7. They're both a negative value. So whether that negative is up top in the numerator or down below in the denominator, it doesn't matter. Here's what's cool about the relationship between distance and slope. Once I find my difference between my x's and my difference between my y's, did you notice up here that this 12 and this 4, this 6, this 4, this 6, this 8, those are the same values that I used in my distance formula. So once I know the change in my x's is 7, and once I know the change in my y's is negative 1, those are the same values I plug into my distance formula. Once I know the change in my x's is negative 7, and the change in my y's is 2, plugging those values in, super easy. Here's the next thing I need everybody to understand. See these negatives? Nobody cares. Nobody cares about those negatives because the minute I square them, they go away. If you are ever doing a distance problem, once you square that change in x or change in y, you should always have positive numbers underneath your radical sign. There should never be a negative number when you're solving for distance under your radical sign, because this negative number squares away. Negative 7 times negative 7 is positive 49. When I leave my radicals unsimplified, it's super easy to see which one's bigger. It's super easy to see which ones are the same. And today we're going to do an activity where you're proving parallelograms to see if they have the same distance or to see if they have the same slope. So if you're being asked to simplify the radical, you have to simplify the radical. If you're using radicals to determine whether or not something is the same length, I don't care if you simplify it or not.
Wait, why did he use the rise over run to plug in the variables? Isn't it x2 minus x1 and y2 minus y1?
It doesn't matter which one I call 1 or 2. So here I did 9 minus 10. I made this my 2 and this my 1. Here I did 6 minus 4. I made this my 2 and this my 1. Nobody cares whether I'm finding the slope from here to here or here to here. That slope is constant throughout the whole line. Make sense? I saw another question. Go ahead.
I was just wondering, am I blind? Because I didn't really think it said find the distance for the line too.
It didn't. It didn't because I didn't want you to. I wanted you to find a slope, and then I wanted to show you how those values, super quick and easy, plug into distance. There are certain things when I work with kids that drive me crazy. When I'm working with kids and I watch somebody take the square root of 0, I've seen, I can't tell you how many tutors that when I'm working with them, they're working with the calculator, and I see them take the square root of 0. Zero times 0 is 0, right? Like, we don't need to take the square root of 0. Please don't ever take the square root of 0, right? That's that kind of thing. I'm like, we need to continue to work Cole's triangle right now. He's like, I wonder what the square root of 0 is. Go, do it, do it. You get one freebie in your life. Everybody right now, take the square root of 0. It's 0, and let that be the only time you ever do it. We need, what, square root of 1 is 1. as mathematicians, we need to develop a number sense. We need to develop that, and that's why Sammy's question, I did this on purpose, forwards and backwards, hoping somebody would say, because we're so rigid in some formulas in math, you've got to do it this way, and other formulas, not so much. Whatever is coordinate pair 1 or coordinate pair 2, nobody cares. You're looking for the rate of change from this one to this one. And this slope represents that rate of change. So I did that on purpose to make you ask. I on purpose did not ask you to find the distance because I wanted to show you this, because I'll have kids do this math and then they'll turn around and do the same exact math. So when I'm sitting at my tutoring table and I'm working with a kid and they do that math for the slope and they subtract the x coordinates and they subtract the y coordinates, and then they go to do distance and they subtract the x coordinates and they subtract the same y coordinates, I wait and wait and wait for the light bulb to go off and have the kid go, oh, that's the same math I just did twice. Yes, you don't have to do it twice because it is the same math. What worries me is when I'm working with a kid and they don't see that it's the same math. Because if you don't see how these numbers are the same as these numbers, you're not thinking about what you're thinking about while you're thinking about it. You gotta pay attention to your math. You wanna get more out of the time you spend doing math, start thinking about what you're thinking about while you're thinking about it. Think about it. All right, take out your homework from last night, please. So come on back, let's talk about, now whether you call this a septagon or a heptagon, I don't care. But what's interesting is we learned from our greedy triangle lesson that each time he adds a new side, we get another 180 degrees. But we want to make sure that we know that every triangle starts at 180 degrees. So I always remember 3 minus 2 is 1, 1 times 180, that's the triangle. So make sure you remember this minus 2 part. It's the number of sides less 2 times 180. You can think about how many triangles can you draw. If I look at some of your papers here, if you're ever in doubt, draw your triangles. Pick one vertex and draw the number of triangles. And I can see that I can get 1, 2, 3, 4, 5 triangles in that septagon. So it's going to be 5 times 180. And here's the interesting part. This is more of a trick question. What's the sum of the exterior angles? It's always 360. In a triangle, 360. In a quadrilateral, 360. Pentagon, 360. Hexagon, 360. Octagon, 360. Circle careful, but you're right, 360. But it's not a polygon because no sides. Nice job. Go show them. Smarty up. You can smarty up for the circle perfection. I have to give you guys more smarties because 5th period gets all the smarties for finding my mistakes. So I fix them by the time you guys come around. So we need to make sure that this chart, hey, you have a quiz on this next class. So, and it's your first grade or your 4th quarter, and I really want your 4th quarter to be solid and strong. So we want to make sure that you're good with how to do a lot of this math. I've got 540 degrees to divvy up. These angles, these 4 angles take up 447 of them. That gives me 93 left for my x. I've got 360 degrees to divvy up. And I can combine like terms and give h a value of 60 degrees. If I have a quadrilateral, my first step here is to don't forget your linear pairs. The hardest thing about geometry is nothing goes away. Everything goes. So we're still talking about supplementary. We're still talking about linear pairs. We're still talking about consecutive interior angles. We're still talking about alternate interior angles.
Wait, for this next class, are we gonna have to remember like septagon, heptagon, and all
Yes.
that?
vocabulary counts. You will be asked to name the shape. And we'll even give you one 13 gone, or 11 gone, or 17 gone. We'll give you one of those. D. So D was troubling. I went to go do D and I was like, oh, so check it out. I know that Z and X are equal to 180. I know that this Z minus 13 and W are 180, and I know that Y and Z plus 10 are 180. So I was fixing to get busy doing a system, and I'm like, oh, if I'm in Pizza Hut, I'm ordering pizza. And what I mean by that is this. If you're in the lesson about the sum of the exterior angles, maybe you should take a peek at your exterior angles. Because if you look at each of these angles, they all have Z's in them. So then I went up here and said, okay, Z plus 10 plus Z minus 13 is 360. Therefore, I can combine my like terms, solve for 1Z. Once I got my 1Z, I could call my X, I could find my X, I could find my Y, and I could find my W. This idea is what we're tapping into with solving systems of equations. You did systems last year in algebra sometime in the winter time, sometime around winter break. And that is where you have multiple equations with more than one unknown, and you use information from one to solve the other. It's the ultimate algebra experience to manipulate to get what you want. You substitute in to be able to solve for what you need. Questions on the first page? Okay. On the back, the most important thing that you understand of this side is that we're talking about a regular polygon here. If I'm talking about a regular polygon, my interior angle measure is going to be the supplement. My number of sides can be found by solving the proportion, because 360 divided by the number of sides is going to equal to the measure of each of those exterior angles. And again, when I'm solving my proportion, I totally cheated. And I swapped my means and just said, oh, 360 divided by 72 is equal to N. What questions do you have about that chart? All right, so next up we have some systems of equations. And I will admit, for some reason, I went the long way on this first one. I don't know why I didn't just put x plus 2 in for y, or in for y. That would have been easier. I don't know, Sammy, you and I talked about this, and I had it on my brain when I was doing my key. But this is what we're doing in a system of equations. And I want to bring your attention, whenever you see these two little lines in my work, that means I took a break and went and did some math somewhere else, and then I came back. Let me explain to you what this is. I went ahead and I solved for x. X is y minus 2. I took y minus 2, and instead of writing x here, I wrote y minus 2. So I took two equations that each had two unknowns, and I figured out a way to express one variable in terms of another so I could plug it in. So notice, I drew my two little lines. I came over here and I did some math, and I came back, and here is where I put y minus 2 in for my x. Once I did that, take notice, all of my variables in that equation match. They're all y's. So now I can solve for y. Y has a value of 8. Then I came back here and I put what I found. I'm like, ooh, I figured out y is 8. Good. Let's put it to work. Because x is equal to that y value minus 2. That's how x is equal to 6. Systems is the ultimate in manipulating. I'm going to figure out how to play the system so that I can solve for my variables, and then I'll go back and clean things up at the end. Y is equal to x plus 2. I plug that in there. Instead of y, x plus 2. Here, y is equal to x plus 3. Instead of y, x plus 3. What questions do you have about A, B, C, or number 4? So here's the deal. My son lives about 30 minutes away in West Falls Church. His wife just bought a new house. Very exciting. I've been there no less than 10 times. If you came with me out to my car and we got in my car and I turned it on and I started to drive, I'm not sure I could get us there. Because I've been there, but I never did the driving. Every time I go with my husband. And he does the driving. And I pay attention, sorta. I listen, sorta. I watch, kinda. But if I had to find my way there without the help of a GPS or a navigation system, there's a very slim chance we're going to get to my kid's house. It's a shame because it's a cute little house too. Do you understand where I'm going with this? Where am I going? If you're paying attention and watching this, and you're like, oh, okay, I remember that from last year, but you haven't put pencil to paper, if you haven't driven the car, you're not going to remember how to do it. Go ahead.
How did you get rid of x on the first one?
Do you see how here I have x is equal to y minus 2? Do you see how instead of writing x here, I write y minus 2? This little equal sign is the most powerful sign in mathematics. This little equal sign guarantees that these two things are the same. You can have an x or you can have a y minus 2. And you're like, I don't know, they're the same. I don't care. Right? That's like me saying you can have a dozen donuts or 12 dozen. You're like, it's the same thing. Right? So x and y minus 2 are the same thing.
Okay.
So I can take y minus 2 and write it instead of x. And that fits what I need.
Alright.
Saw another hand. Donovan, did you have your hand up?
I figured it out.
Okay. All right. So we'll talk about these down here. This question bothered me because we needed to have been given that's a parallelogram in order for us to do this math. It says solve for each variable and justify the equation you knew. And if somebody tells me it's a parallelogram, then I can set these equal to each other and solve. But without that conversation, I got no math. I can set these two sides equal to each other and get each value. But until somebody says, hey, by the way, Tracy, that's a parallelogram, I don't have any math to do. Are you with me on that? So that bothered me about that question. Let's talk about this question. It was really bothered that they called this angle 110 degrees. Because it's an acute angle. But it doesn't change that the math can still be worked out. Same thing here. This ends up being 109 degrees. So that math doesn't work out with that picture, but that's okay. Anything you need help with? Anything you want to talk about? So this is a little bit different. So this is a little different. We have this pattern that's been happening where if we're given parallel lines, we have all these cool things, and then the converse says, if you have the cool things, you can prove the parallel lines. We followed the same pattern with congruent and similar triangles. But now we get to parallelograms, and instead of calling these a converse, we end up giving them their own theorems. So everybody join me. So when we talk about the definition of a parallelogram, if you have a quadrilateral, and break this down, your quadrilateral is going to be your polygon with 4 sides. If each of those opposite sides is parallel, then you're going to have, by definition, what we call a parallelogram. So if you scan through the next 1, 2, 3, 4, 5 theorems, you see that it's all of these conversations where if blah, 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 then it's parallelogram. Then it's a parallelogram. Then it's a parallelogram. So what I'm going to ask you in your groups to do, I'm going to divide you up, and I want each of you to tease out how each of these theorems is justified and proven. Our group over here to go first. So this theorem says if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Spokesperson over here, wow us and tell us how we can justify that shortcut. Go.
Okay, well, first you draw your diagonal. And then you can use the side theorem to figure out that the two triangles are congruent.
Got it?
Then you can use CP to prove that all the angles are congruent. And then you can use alternate interior angles to prove that both the sets of sides are parallel.
I love it. So I heard side congruence. I heard CPCTC. And then I heard alternate interior angles. And those alternate interior angles give me my parallel lines. My two sets of parallel lines, by definition, give me a parallelogram. Thank you, Cole, for helping us review for the SOL.
Thank you, Cole.
Thank you,
I
Cole.
love you, Cole.
Very nice job, Cole. Go put a smarty up. All right, next we get to my group in the back. Who is your spokesperson? Emery points to Juan Martin. You've been nominated. There he goes.
Consecutive interior angles.
Okay.
It's like A and B out of 10 and B.
All right. So if we talk about this, we get A and D adding up to 180, but we don't know that. That's this group's jam down here. Right?
Yeah.
Okay, so we gotta think about this for a little bit. How do those angles get us to parallel sides? What if I said that? Does that help?
Yeah.
Go ahead. What does that give me?
Alternating interior.
Yeah. If I have these alternating interior angles, if this is supplementary to this one,
That means that one's.
right? So now I have congruent supplements. Are you okay with that?
Yep.
Congruent supplements. And that's how I end up getting my alternate interior angles. And that's how I can end up getting my lines parallel, and I can repeat that process on the other side too. Thank you, Juan Martin. Go put a smarty up. All right, next group. What you got for me? Who's my spokesperson?
Mason.
Donovan, go.
Oh, what?
Oh, I heard your voice that said I am.
No, I said.
I definitely heard your voice. Go.
Yes. Okay, so it's saying that A and B are supplementary, and A and D are supplementary.
Good job. Keep going.
Because they are like consecutive interior angles.
I love it. If I have consecutive interior angles that are supplementary, then I know that my lines are parallel. So basically what we're doing is justifying each of these shortcuts. Imagine your friend saying, hey, I got a shortcut home. And you're like, how do you know it works? You're like, trust me, because it'll take us through this path. It'll take us through this path. You got to be able to let them know how it works. Thank you, Donovan. Go put a Smarty up. Aylin, your group is up.
Okay, so we know that there's two congruent triangles by side angle side, and we can tell that it's parallel because of alternate interior angles.
I love it. They did vertical angles here. So they got congruent triangles by side angle side. Then they used CPCTC to get this set of alternate interior angles. Once they get that set of alternating interior angles, they can repeat that whole process with the other two triangles, these smaller triangles, and then they can get those same conversations necessary to prove our other two sides. All right, Sumner's group, go.
Alright, so first can you extend the line so it just makes everything easier. So we know that angle ADC
Mm-hmm.
is congruent to angle nowhere AB because they're corresponding. And then what did I do? And then we know that angle nowhere AB is congruent to angle ABC because they're opposite interior angles. And then if we put a diagonal and we make it triangle ABC and triangle ABC, then we can use that as a transversal and get that angle DAC is congruent to angle ACB. And same thing to get DCA to
Or reflective property to
Yeah,
get the line.
whatever
And then
the other one. And then we got AAA congruence, and then CPCT gets us AD is congruent to BC, and then we can use theorem 88 to get.
Very close. Very good. Go put up a Smarty. Did you know where they went south? Here's the hardest part. Keeping track of what I know and what I'm proving. He used
the sides that you don't know are parallel.
So I have, think about what you're given. You're given, so as far as, I know these two lines are parallel, so I was good with these two angles being congruent, but nobody told us these two lines were parallel. But I let him keep going because guess what? He never needed this one. Because he used these parallel lines to get, and this transversal to get these
Oh, and then we had
alternating interior angles, right?
We confused ourselves.
And then you had this,
I went like,
you had this transversal congruent to itself, and then you had this side. So you have side angle side congruence. And side angle side, once you get the triangles congruent, then you get everything that you're missing. Do you see?
Yeah.
So good job. There's a lot of information in there, but what makes me so button bursting proud is all of that geometry that just came out from all of you groups. Because that's all the stuff that you guys have been learning since vertical angles to supplementary to parallel lines, alternate interior and consecutive interior. All that stuff still counts and it all matters. That's good stuff right there. All right. If you turn the page over, you've got some practice problems. So go ahead and attack these with your group mates, and then we'll come back and check them out. Go. All right, so let's just talk about these first two. The painting the stained glass window has the shape shown at right. How you know it's a parallelogram? Because I've got two sets of opposite sides that are congruent. So that's it. This one's kind of. So those of you who are like sitting around not picking up your pencil and not jumping in, this was an easy one. When we talk about a gemstone, whether we're talking about a piece of jewelry, a ring, a necklace, whatever, it's cut so that one of its facets, that's one of the sides of it, or one of the stones in that has four sides. When I look at the measures of the sides, if they're telling me that they're consecutive angles, if they use the word consecutive, that means that they're all in that order around, which means it can't be a parallelogram because I don't have opposite congruent sides. What do we know that this shape is called? We will learn in a couple of days that's a trapezoid. All right, so here's the deal. Lots of conversation about these justifications, and I'm with you. I want the fastest, most efficient way of going about doing everything, because that makes sense to me, but I don't want to cut corners, and I want to make sure that I am learning. When I'm doing this activity, if I want to prove a parallelogram, how about this, Nora? It's even shorter. If I want to prove a parallelogram, I know I've got six things, 6 methods, 6 justifications, 6 reasons that can justify it being a parallelogram without peeking at the front. See if you can, just with your group, talk about and list them all. Don't peek at the front. Your mark as I go. So practice. Come back. Practice being able to list all 6. Practice. If you know there's 6, and it's funny, different kids get hung up on different ones. I know which one is the hardest one for me to remember. I get 1, 2, and 3 knocked out right away. 2 sets of parallel lines, opposite parallel sides, 2 sets of opposite congruent sides, 2 sets of congruent angles. This is my shorthand to help me remember. What's this stand for?
The guys in the middle are congruent.
Bisecting diagonals. Bisecting diagonals. If this picture doesn't make sense to you, maybe put BIDIA, right? Bisecting diagonals, whatever makes sense to you. Consecutive angles have to be supplementary. This is the one, that's the one that stumps me. I always get the one side parallel and congruent. So you should be able to, if somebody gives you a quiz paper like you're getting next class, I'll say it again. If somebody gives you a quiz paper like you're getting next class, if you're worried about forgetting those 6 features on your paper, just the same as I told you, quick write Sokotoa, get it down on the paper, study, get these in your head. And if my notations don't make sense to you, don't use mine, come up with your own. Do whatever works. Do whatever works for you.
What are you trying to say for number 6?
One pair of sides is parallel and congruent. So that when I need to, can I prove each parallelogram, each quadrilateral is a parallelogram, I can say yes, and I can talk about bisecting diagonals. My number 4 here. Now, if you have a quiz or a test, I don't want your number 4. You're going to have to spell it out. But for the purposes of doing homework, if you want to do it that way, you can. How about this one? Which one is this? Why?
I got one pair.
Only one set of angles.
Yeah, nobody told me. Nobody told me what these other angles. Or I don't have anything that's supplementary. So I need more information than just one set of angles. How about this one? Yes or no? Which one?
Oh, I found
2 sets of opposite congruent sides. How about this one? Sumner, what do you think?
For
What's my
number- for E,
justification for D?
it's just the definition of a parallelogram.
Yep, it's 2 sets of parallel sides. I'll buy that. How about this one?
That's
Yeah, it is. Good look. I can. Or 6.
Oh, yeah. Wait, this is the parallel opposite line. It's like, oh,
Yeah.
Now here's what I want you to do. I want you to have in your notes what is not going to be an example. Draw yourself a parallelogram. Give yourself one set of parallel lines and make the other set congruent. Here's why this is a no-no. If I don't have a set length for this, no one says that I don't have a trapezoid. If I have one set of parallel sides and one set of congruent sides, nobody tells me whether that's a trapezoid or a parallelogram. So if it's the same set, is the same length and parallel, then yes it is. This is not a parallelogram. This one always surprises me that kids don't get this one. Because they're like, no, that doesn't have 2 sets of opposite sides that are congruent. I'm like, yes it does. And they're like, no, because it's a square. I'm like, so just because all 4 sets are side, no one said they had to be different. Do I have 2 sets of opposite congruent sides? Yes, I do. All right. Down here, for what values of x and y must each figure be a parallelogram? Your first thing is going to be to justify whatever equation that you use. So do you see I have y's and y's here? I'm going to go ahead and look at reasoning number 5 to write my equation, solve for y's, and then I could go ahead and solve for x's. This one's going to be tricky because it's a system. If I have 2 sets of opposite congruent sides, like not my justification number 2, I have 3x plus 1 is equal to y. 5x is equal to 2y minus 5. I'm going to have to use a system of equations to solve that. Here I have some conversations about my bisecting diagonals. That's definitely reason number 4. And here again, my opposite sides that are congruent. That's definitely going to be reason number 2. So take your time, please, and go ahead through and solve these. Don't be a passenger in the math car. Get in the driver's seat, pencil to paper, do some math. Go. We've got one more thing to do today, but I want to make sure that you have the answers to these so that you could go back and do the math. I need you doing the math. If you're not doing the math, you're not learning. Sound okay? All right, last thing for today. I want you to go back to your warm-up. Back to your warm-up, and I want you to notice that we gave you, I want you to notice we gave you the same ordered pairs and the same picture, but we gave you a method 1, we gave you a method 2, and we gave you a method 3. So if you're sitting in a group of 3, each one takes a different method. And what I want you to do is I want you to use, hold on, I want you to use distance and slope and our parallelogram theorems to prove that your parallelogram, that figure, that quadrilateral is a parallelogram. If you have a fourth member, what I want you to do is go back to your quadrants 1, 2, 3, and 4. Quadrant 1, do method 1. Quadrant 2, method 2. Quadrant 3, method 3. Quadrant 4, it's your choice. Choose your choice for quadrant 4. But I want you to take the time and I want you to prove it's a parallelogram by using
Determine that both sides have its own slope.